Welcome back. In this video, we are going to finish off our leaf and then begin working on our internal nodes. We finished the last video with some kind of unexplained errors. Turns out the one in update was that this parentheses was just in the wrong location, and that was what was causing the problem. The interactions between our test suite and metals is one that I'm not going to fix, so instead I will just run tests inside of SVT. I added a few tests, but I also added one more that adds 5 values into it. And I guess if I get rid of that, we can see that all of our tests get rid of it and don't test for it. That now passes. But if we try to add a 5th element to our collection, we get this, and that is because we have an unimplemented method, which is the fact that we're coming here. So we need to make our internal node if we hit this point in the code. So how do we do this? Well, the first thing we have to do is we have to make a new leaf that includes just the new element. Okay, so val, I'll call it the sibling because it is the sibling to this leaf, is a leaf around an array sequence that has just that one element in it. By the way, I also offline added some additional class tags in places, otherwise it was unhappy making array sequences. So I have another leaf, and then I need to make an internal node that contains as its first thing, it points to this, our leaf that is completely full, and the second thing that it points to is the sibling. Okay. Let's see. Oh, and I forgot, it's at level 1. Because this internal is one step above a leaf, it will always be level 1 there. What does that do for our tests? Now we shouldn't have the unimplemented. In fact, I can probably, since I still have this to interact with here, not implemented missing. What we're getting is an unimplemented missing now should be slightly different. The apply on the internal, because in my tests, and in fact we can demonstrate this. So the problem is that line right there where we try to call apply and get the val out of our internal. Oh, actually, no, all of them will be unhappy because at this point, V is an internal node, and so all of these gets don't work. So I guess I can comment all of them out and show that we're able to build it, but we're not able to get anything. So that's, yeah, not a great test. We're just showing, hey, it doesn't crash anymore. So in order to make that test pass, I have to write some of the implementation in my internal. In particular, I have to write the apply method in my internal. Well, turns out the apply method in the internal has a lot of similarities to the apply method in the leaf. But instead of just taking the index and ANDing it with our bit mask, we need to downshift the index by an appropriate amount. And we had started writing this previously. Whatever our level is, we need to multiply that by the bits in alphabet. And this is not called data here, it's called children. So what we're doing is we're taking our index, we downshift it however much we need to, we AND off the bits that we actually care about, we index our children with that, and that gives us the appropriate child at which to call the apply method on the same index. Okay. I'm manually calling apply here. This is actually perfectly valid code to do it this way, but given how far out that is, I think it's going to be more readable if we manually call apply. So what does that do for our tests? Apparently I still have point and click capabilities. There we go, this ran now. So I was able to index and I was able to get off the 5, which is now sitting in a second leaf there. What about our other methods? I have this tendency to start with the things that are easy and work my way up. So the next easiest is probably our size method. It would be good to check to make sure that we have a size that is 5 if we've added 5 things. Now, how do we get the size of an internal node? Because remember, size is how many total elements we have. It's not the size of the array, because in this case, our children, the first element of the children in this example, the first element of children has 4 things in it, and the second element has 1. And so we should be getting an answer of 5. So an inefficient way to do this would be to do a children dot, this is actually going to be a rather inefficient way to do it. Get all the size of your children and add them up. Okay, that would work. But then we wind up running through the entire tree, and it's going to be very inefficient for a large try. So how could we do better about this? Well, it turns out we know that every child except for the last one, so children's length minus 1, all of those are completely full. Okay, and full here means that they have a number of elements that is 2 to the power of bits in alphabet. And you might recall from an earlier video, we can calculate 2 raised to the power of bits in alphabet by doing an upshift. So if bits, right now our bits in alphabet is 2, but if we were to increase it to 4, this would wind up being 16. And so all of the ones that, other than the last one, have to be full, otherwise we wouldn't be in that last one. That last one we can't a priori know how big it is, so we need to add on the children.last.size. Okay, and that will give us the total size that's in here. We can augment our test doing an assert equals of v.size and make sure that it returns 5 to us. Cool. Okay, so we have an apply method, we have a size method. It turns out updated is actually easier than appending, so we could test that. As with the leaf, a lot of the code is similar to apply, but we're making a new internal node. We're making a new node that's at this level with one of the elements updated. So instead of recursively calling apply, we're going to recursively call updated on the appropriate child. So we would need to do children.updated, and the first argument to it is the index, and I'll make sure I get the right set of parentheses there. And the second is the value that we want to update it to, which is E. And this needs to be wrapped inside of an internal at the same level as this one. Oh, actually, updated. Does an array sequence not give us the... I'll have to come back to that because, oh, it's, nope, I know why. Because it's not adding it's children updated with one element replaced. So I should probably go ahead and copy this. And let's go ahead and put some curly braces on this. Val child index is that. I need to give it a nice name. That is the index inside of children that we want to change. And so I want to get children updated at the child index, and the value I want to set it to is children sub child index dot updated to index comma e. So I'm recursively calling the update. I did need that parentheses there and that parentheses there. Okay. I'm recursively calling the updated on the child at that location and using that result to replace the child at that location. And getting back a new array sequence and the same level. So that is updated. We should be able to augment our test fairly quickly. Val v2 equals v dot updated. Let's go with index 2 and we'll stick the 99 there. And because it's index 2, I'm going to copy this line of code to make sure that we didn't mess with our original. And then on v2, I want to make sure this has 99. And bingo. Okay, so that's good for this video. We have everything except for the add on an internal implemented at this point. We'll come back in the next video and we'll do that.